Electricity is a dynamic physical force that drives our modern world. To understand it, we must explore three core quantities: current, voltage, and resistance. Let us uncover the physical perspective of how electricity truly works. To understand electricity, we must look at the atomic level. Every atom has a nucleus of protons and neutrons surrounded by orbiting electrons. In most materials, these electrons are tightly bound to their nucleus, unable to move freely. But in conductors, like metals, the atomic structure is different. The outermost valence electrons are only weakly bonded. These loosely bound electrons detach from individual atoms, creating a sea of mobile negative charge carriers. This ability of electrons to move freely through the metallic lattice is the fundamental reason why conductors carry electric current. When we think of electric current, we might imagine electrons racing rapidly through a wire, but individually they actually drift quite slowly, constantly colliding with atoms. However, because there are trillions of free electrons, their collective movement creates a massive instantaneous net flow of charge. This macroscopic flow is what we call electric current. We define current denoted as I as the rate at which electric charge flows past a specific point over time. Mathematically, I equals the change in charge, Q divided by the change in time t. It is measured in amperes, where 1 ampere equals exactly 1 coulomb of charge moving every second. To understand why electrons flow, we must look at the driving force behind them: electric potential difference, commonly known as voltage. Imagine 2 points in space. If one has a higher electrical potential energy than the other, an electric field established between them. Voltage is not just a pressure. It is precisely defined as the amount of energy required to move a unit of charge between these 2 points. It is measured in volts. 1 volt means that 1 joule of energy is expended to move 1 coulomb of electric charge. This potential difference creates the fundamental electric field force that pushes electrons through a circuit. When voltage pushes electrons through a conductor, they don't travel in a straight, unobstructed line. Instead, they constantly collide with the vibrating atoms of the crystal lattice. This is the physical origin of electrical resistance. Each collision scatters the electron, slowing its forward progress and transferring kinetic energy to the lattice, which we feel as heat. This opposition to current flow is an intrinsic property of the material, measured macroscopically in ohms. The more collisions occur, the higher resistance, and the harder it is for current to flow. We've seen that voltage provides the push, resistance opposes the flow, and current is the resulting movement of electrons. In 1827, Georg Ohm discovered that these three quantities are elegantly linked by a simple mathematical formula: V equals I times R. This is Ohm's law. It states that the current flowing through a conductor is directly proportional to the voltage applied across it. If we plot voltage against current for a material with constant resistance, we get a perfectly straight line. This is a linear relationship. Double the voltage, and the current doubles. The constant slope of this line represents the resistance itself. This simple law gives us the predictive power to understand and design any electrical circuit. To summarize, electricity is governed by three fundamental physical quantities. Voltage provides the push, current is the flow of electrons, and resistance is the opposition to that flow. Together, they form the foundation of all electrical systems. Thank you for learning with us.